Okay, good morning everyone. My name is Pablo Nogales and with my colleague Victoria Prieto, we are going to present our project, which is called Numerical Aerodynamic Study of a VTOL UAV for a wide range of attack and sideslip angles. This work is framed inside the Emergentia project. But first of all, what is Emergentia? Emergentia is the acronym for the full title Development of an Unmanned Convertible Aircraft for Rapid and Efficient Deployment in Emergency Situations. This project arises from the fact that emerging technologies are radically changing traditional operating procedures in disaster relief and emergency response management. In particular, UAVs are proving themselves extremely useful in search and rescue missions. They bring very advantageous capabilities such as rapid response, remote operations, transportation of equipment, monitoring of wide areas, and multi-sensor deployment. Project Emergentia proposes to explore the use of a birotor convertible fixed-wing aircraft with VTOL capability, specifically designed for some missions, which are search and rescue operations in emergency situations. This prototype would combine the virtues of a fixed-wing vehicle, gaining greater range and endurance, and also the benefits of a rotary wing aircraft, performing hovering flight and vertical takeoff and landing. And it would be able to carry out the transition between both modes of operation in flight. The aircraft would be easy to operate and fast to deploy. With this aim, guidance, navigation and control algorithms will be developed considering the requirements of SAR missions. In addition, to test the robustness of the different autonomous control strategies, high-fidelity 6-degree of freedom simulator is required. Regarding this, it becomes a must-have to achieve complete aerodynamic and propulsive models for the entire flight envelope of the aircraft. For this reason, the project we presented here has the main objective of characterizing the whole aerodynamics of the prototype for the 3 flight stages it has been designed for, which are axial flight, transition phase, and cruise flight. With this aim, it has been conducted numerical analysis on the model varying the angle of attack and the sideslip angle. For these studies, the geometry has been created on CATIA and exported to ANSYS Fluent, where the CFD analyses have been developed.
As we have been able to see during the previous slides, we have considered 2 models, but in the end, only the one on the right, CP1 model, has finally been chosen and studied. For this model, we have different values of the specifications, let's say, and especially we should focus on the sweep angle. That is a forward sweep angle, and that for future experiments, for future analysis, we are going to eliminate. So we are not going to consider a sweep angle. The original full-size model had to be scaled in order to conduct the wind tunnel experiments, and as we are going to reproduce the exact same disposition, we are using the same dimensions. 2 main criteria were considered to select the appropriate scaling factor: the wind tunnel blockage factor and the size limitations of the 3D printer that would be used to print all the parts. With these 2 criteria in mind, a 1:4 scale factor is chosen in order to make the blocking effects negligible. The final dimensions of the test aircraft are a fuselage length of 42.3 centimeters and a wingspan of 62.7 centimeters approximately. In what refers to the setup, the wind tunnel is an open circuit one of 23 meters length, divided into 3 sections: the contraction chamber on the left, test chamber on the center, and the diffuser. The test chamber, which is the most important area for the experiments, has a length of 50 meters and a rectangular section of 1.4 meters wide and 1.8 meters high. In the picture, we can see a panoramic view of the tunnel that has been used for the experiments and that we are going to represent on Fluent. As in the numerical analysis, we are only going to focus on the test chamber. This means that we are going to forget all the other parts of the tunnel. The reason for this is that we want to reflect the exact same conditions as we have disposed in the experiments, so the results are as near from reality as possible.
Now we are going to talk about the construction of the fluence model. Firstly, it has to be considered that the geometry was originally designed in CATIA, so it needed several modifications to be adapted for the CFD analysis. Initially, it was carried out the refinement of the zones that might induce failures, like severe change of curvatures or angled intersections between different surfaces. However, this process generated the division of the external structure in a lot of different surfaces that represented an important source of meshing errors. To solve this, all these zones were meshed. Taking advantage of the important lines, the new union system strategically divided the geometry into the major parts of the plane. This way, each component surface could be meshed independently. Speaking now about the meshing process, obtaining an adequate mesh of the model is essential for the analysis. This mesh had to be dense and structured enough to ensure a good precision in the results, and its elements must be concentrated in the most relevant zones. However, using too many elements could imply a huge computational cost, which means large processing times. Therefore, this is an important aspect that needed to be optimized. First of all, the mesh had to be adapted to the aircraft shaped in a precise way. This is difficulted by the complex geometry of the model, especially in the zones with marked curvature and abrupt inclination changes. In order to solve it, the mesh density has been increased in these parts, which especially affects the fuselage wing and fuselage tail joints. Subsequently, the mesh of the leading and trailing edges in the lifting surfaces has been reduced. These zones are the most relevant for the lift and the drag force of the aircraft. Therefore, it has been imposed a larger number of elements around them. This action has also been carried out in the end zone of the fuselage in the middle part of the V-tail. With these operations, the mesh around the plane is completely defined. Characterizing the external surfaces of the fluid domain, the definition of the entire mesh is finally obtained, resulting in about 2 million elements. Finally, it is important to correctly define the boundary conditions. To do this, all horizontal and the tunnel entrance walls are defined as velocity inlets, and the tunnel exit as a pressure outlet. The reason why there are a total of 5 walls defined as air inlet is because, unlike the test carried out in the wind tunnel, in the program the fluid domain is the one being rotated instead of the main model, as it happens in the wind tunnel. For this reason, if a condition is set as a wall in the horizontals, as it might seem feasible at the first instance, when increasing the angle of attack or the Sideslip angle, no wind would reach the model. Therefore, the analysis carried out wouldn't be sufficient.
Once the mesh has been already defined, it's necessary to take into account the selection of the turbulence models. So, although in the beginning we consider diverse turbulence models, finally only 2 methods of analysis have been chosen to be studied. That are the K-epsilon turbulence model and the K-omega turbulence model, as were suggested to provide better performance with less computational cost. Initial studies were conducted considering first the K-epsilon turbulence model, with results that were not completely satisfactory, as it was defined that the values of E+ registered with the mesh were around the unit order, when this method is most recommended for more elevated values of this parameter, around 50. To solve this problem, we enabled the wall treatment function, but even with this option, there were poor results and even divergences for certain values of the angle of attack and Sideslip. For this reason, we decided to use, instead of this first model, the K-omega model that is supposed to better work with an E+ around the unit order. It was observed that after having a fixed tendency but not fulfilling the converging limit, oscillations occurred, and it did not converge, not even for high values. So we had to take another decision. For all this reason, we decided to use the transition that allowed us to solve all these previous aspects. But the main problem of this was the increase of the computational cost. That was the reason why we had chosen at first instance the first model. In addition to this, we have to take into account other considerations. First of all, the choice of the speed value, the characteristic one. This is around 11 meters per second. That was chosen in order to use the exact same speed as we were using in the tunnel, and it was selected within 6 velocities. But the reason why we chose this one was that over 50 degrees for the angle of attack in higher speed values, we obtained some oscillations in the model that made us disturb the measures obtained. So we could not use this measure experimentally, so we had nothing to compare with. Also, it's necessary to mention that we have done the analysis, the numerical analysis for variation of angle attack in the rate of between minus 30 to 90 degrees, each 5 degrees between each measure. And also, it's not in the slide, but we have also made from 0 to 40 degrees for the sideslip angle, each 10 degrees. Also, we have considered some wind tunnel corrections. We have considered all of these corrections, but I'm only going to speak about the solid blockage. That is the most important one. This is the solid blockage. Basically, what we can see, we can observe is the increase of the speed around the model, around the aircraft that we are introducing in the wind tunnel. The reason for this increase, this acceleration of the air, is that we are reducing the area through which the air passes. So as we reduce the area, the speed has to increase, so the air is accelerated. What we do to see if this effect can be or not negligible, we calculate the increase of this speed, and we compare it to the actual speed, medium speed we are putting into the wind tunnel, or in this case, into the numerical analysis. As we can see, the epsilon SB is so small compared to the real speed value that it can be neglected.
Once the fluent model has completely been set up, we can picture some representative obtained results for the aircraft 1 configuration and selected characteristic speed. We can observe the graphics of lift and drag coefficients for several angles of attack, and it is possible to compare both CFD analysis with the experimental tests in the wind tunnel, showing a really good trend correlation and so proving the validity of the model. The next figures depicts of some representative CFD results of the study conducted. A velocity contour example for alpha equal to 5 degrees here at the left, and the streamlines for a sideslip angle beta equal to 20 degrees at the right side.
Just to conclude, after doing all these numerical analysis and studies, we have realized that we are lacking a lot of information. So we have decided to do a more exhaustive study, which means doing a numerical analysis of the separate models of the aircraft, wing, tail, and fuselage. Also, we are going to conduct the same exact analysis we have already done and the ones we are speaking about right now for another model with a straight wing, because we have already results of the experimental analysis, experiments in the wind tunnel for this second model. And finally, we are thinking about changing the software we are using for these simulations, because that will allow us to rotate the model instead of the fluid. And that's all. Thank you for hearing us and for watching us, and hope to see you in the conference.